Hello everyone, welcome to a new module in our machine learning course. So in this lecture we will discuss regression in machine learning. So regression is one of the foundational concepts in predictive modeling. It helps us predict continuous outcomes based on input features. So regression, simply put, is the process of predicting a continuous outcome based on input variables. It is different from classification, which predicts categories. So regression models, they find applications in various fields, from predicting house prices to estimating stock values. Now, there are different types of regression models. Each will be suited for a different scenario. So we have simple linear regression, which assumes a linear relationship between an independent and dependent variable. And there are also other types of regression, like logistic regression, polynomial regression, ridge regression, and so on. So let's start with simple linear regression, which we are seeing in this figure here. So this figure is a scatter plot between an independent variable, which is the horsepower, and a dependent variable, which is the amount of time the car takes to accelerate. So we can see that we have a negative linear correlation between these two variables. So the higher the horsepower of the car is, the lower the amount of time the car takes to accelerate. So simple linear regression model here is represented with the blue line here, which represents the relationship between an observed variable and a predicted one. So based on the observed horsepower value of the horsepower of the car, we can predict the acceleration. And here we also define the residual, or the loss, or also called the error, and is simply the difference between the observed value and the predicted one. So the observed value here is this data point, which is the actual value in our training data, and the predicted value is what the linear model has predicted. So it's the point on the line of the linear model. And then the difference here, which is this line, is the residual, is what we call the loss, or also the linear regression residual. So linear regression is a simple yet powerful method for predicting continuous outcomes. So we have simple linear regression, which involves one predictor variable, and the equation of the model is a simple equation of a straight line. So it is y equal b0 plus b1 times x. So this simple equation forms the basis for linear regression. And then on the other hand, we have the least square regression, which is a broader concept that refers to the method that we use to estimate these coefficients, or these parameters, in the simple linear regression equation, which is b0 and p1. So the main idea behind least square regression line is to try to find the line that best fits the data points in a way that the vertical distances between the observed variable and the predicted one, which is what we called previously the residual, is minimized as much as possible. So this can be achieved by minimizing the sum of the squared residuals. And so once the coefficients are estimated, then the regression line can be plotted on a scatter plot of the data points. So the line represents the best linear approximation of the relationship between the independent and the dependent variable. So it serves as a predictive model that can be used to also make predictions for new and seen instances in the future. So in practice, there are many considerations when working with regression. So the data itself has to be pre-processed, so we have to make sure we go through the data preparation phase where you clean your data and you handle any missing values, as well as scaling and normalizing the features. And then the second step will be to visually plot the data and make sure that it shows a linear relationship between the variables in order to use simple linear regression. Because as we said, this type of model only works for linear data. If you are representing or if you are inspecting two features that have nonlinear relationship, then a simple linear regression model will not perform good for that type of data. And so there's also something called the correlation coefficient, which can measure the direction as well as the strength of the linear relationship between those two features. And the coefficient is a unitless value that falls between -1 and 1. So if the correlation coefficient has a value that's close to 1, then you can say that those two variables are strongly positively correlated. And you can say the same thing if it's near -1, then you can have a negative correlation between the variables. So as I said before, plotting the data or using a scatter plot to visually inspect the data is a crucial step before deciding to use a simple linear regression model, because calculating the correlation coefficient alone may not be a good indicator that you have a linear relationship between the two features. For instance, in this example, if you calculate the correlation coefficient here, it equals to 0.81. However, if you plot visually those two variables, you can see that they do not have a linear relationship. So using a simple linear model here will not perform well. So now we shift to another type of regression model, which is logistic regression. So unlike linear regression, logistic regression is a classifier. So it's a classification algorithm that is used to predict the probability of a binary outcome. So when we say a binary outcome, we speak of a classification problem where you have two classes or two labels. For instance, you're trying to classify cancer versus non-cancer, COVID positive or versus COVID negative. So it's a binary classification problem. So here it's a good idea to try logistic regression to solve this problem. So despite the name, which says logistic regression, this type of model is mainly used for classification, not for regression. So meaning it allows us to predict a categorical outcome from numerical features. So logistic regression tries to predict the probability of a binary outcome, as we said. So the outcome can be 1 or 0, yes or no. So it achieves this by using the logistic function, also known as the sigmoid function, which can be seen here in this figure. So it maps the predicted values between 0 and 1. So the output is the probability of the instance or the observation belonging to a specific class. So training a logistic regressor or a logistic regression classifier involves maximizing the likelihood of observing the actual outcome given the input data. So this is done through the maximum likelihood estimation method, and the coefficient themselves of the logistic regression model can be estimated to maximize the likelihood function. And there are specific methods to do that, and an example is the gradient descent optimization method. So the logistic function often referred to as the sigmoid function as well, is the core of logistic regression models. It is represented by the equation seen here in the figure, and the P here represents the probability of the outcome belonging to class CS, or the probability of the outcome being 1 given the input X. So training logistic regression, as we said, involves trying to maximize the likelihood of observing the actual outcomes given the input data or the input features that you have. So the Z, so here it's E minus Z over 1 plus E2 minus Z. So the Z here is the linear combination of the predictor variables. You may have multiple variables as input to classify the output, and you can build a linear relationship between those predictor variables and use them as input to the logistic regression equation. So regression analysis finds wide-ranging applications today across different fields and industries. So it serves as a powerful tool for predictive modeling, understanding relationship between variables, and making data-driven decisions in different disciplines. So I encourage you to investigate this more, do the assigned reading and activities on Zybooks as well as the labs, and think of applying these two models to your final projects.